All right, continuing from where I was, the young scientist Nakamura determined to use these 3,5 semiconductors, gallium nitride, which had this very big barrier to entry. The barriers consisted of, as I said, lack of ability to dope, lack of ability to grow, and lack of a substrate which was lattice matched. So fortunately for Nakamura, he was a very hard worker and he was a genius. But in addition, he happened to be at the right place at the right time because two other Japanese researchers in universities were also working on gallium nitride, and they happened to come forward with two key ingredients which really helped Nakamura succeed. And in fact, the three of them won the Nobel Prize together. So Nakamura and these two other scientists in Japan were able to A, grow gallium nitride, B, dope gallium nitride p-type, and C, find a substrate on which to grow gallium nitride. So first of all, let's talk about doping. Gallium nitride, being a 3,5 semiconductor, is amenable to the same type of doping that other 3,5s would use. So if you're going to make a gallium arsenide LED, a dopant for N-type could be silicon, and we've discussed silicon before. If silicon substitutes for gallium, it's a good N-type dopant. Another potential N-type dopant is germanium. Again, it can substitute for gallium. These two dopants are actually the most heavily used N-type doping in the gallium arsenide system, and in fact they also were amenable to N-type doping in the gallium nitride system. So N-type doping was not a big deal. The problem was in terms of P-type doping, the P-type dopants used to dope gallium arsenide really would be zinc or perhaps cadmium. And these 2+ dopants simply didn't work in gallium nitride. And that was a major barrier to gallium nitride use. In fact, that was one of the key reasons that other research groups around the world didn't take gallium nitride seriously, because they assumed it really couldn't be doped p-type. Well, one of the university professors in Japan found a way of doping it p-type, and the element he chose was magnesium. Now, magnesium is a group 2 element. Group 2 elements weren't terribly popular as p-type dopants, and in fact magnesium was better known to have an octahedral symmetry, where it would be sitting with 6 nearest neighbors of anions. Like, for example, magnesium oxide would be magnesium with 6 nearest neighbors of oxygen in an octahedral arrangement. That's how magnesium oxide is formed. It's not terribly common for magnesium to have 4 nearest neighbors, which is the number of nearest neighbors you need in the case of gallium nitride, because gallium nitride is a gallium ion surrounded by 4 nearest neighbors of nitrogen in a tetrahedral bonding symmetry. Nevertheless, magnesium turns out to be able to accommodate to that tetrahedral bonding symmetry, provided you heat the crystal containing the magnesium impurity to a sufficiently high temperature, and people weren't aware of that. So it was found that if you substitute magnesium into gallium nitride and you heat that doped material up to approximately 900 Celsius, which is extremely high in temperature for most 3,5 semiconductors, that magnesium can, in fact, accommodate to the gallium site and produce a hole. Now, that was a major achievement. It's not capable of very high doping concentrations. It's limited in the 10 to the 16, 10 to the 17 per cubic centimeter range, but sufficient for a good LED. So that was one breakthrough. Another breakthrough was the ability to grow gallium nitride, and this is where Nakamura himself really led the way. It turns out that the MOCVD technique, the metal organic chemical vapor deposition technique, is capable of growing gallium nitride, but the growth was very poor. You would get very uneven growths, partly because the substrates are hard to find, but partly because the gallium and the nitrogen don't easily crystallize. So Nakamura struggled for a long time trying to adapt the MOCVD process to be usable for growing gallium nitride. And he would design and produce his own furnace tubes. He had the ability to create his own quartz furnace tubes and rejig the way his furnace was organized and the way the gases flowed in and the way the gases flowed out. And because he did this all himself, working 12 hours a day, he had complete control, and he could change an experiment which would have taken another company months to do. He could do it literally in a couple of days. He didn't have to wait for a technician to respond to a series of drawings, to get approval, and then to create something different, and then to try again, which would be the normal corporate way of doing business. He just did stuff himself. And he came up with a very innovative tube design where in the MOCVD process, the furnace normally sits around the tube like this. Well, Nakamura created an extra inlet which actually came in from the side, and the substrate would sit down there in the flow, and he'd introduce one gas coming in that direction, which could be a TMGA source. Remember, that would be trimethyl gallium, an organic material with 3 methyl groups containing a gallium atom. And then the other flow could be nitrogen, and one nitrogen containing gas that happens to be very effective is ammonia. So that additional component added to the flow of the TMGA would react at the substrate to grow, for the very first time, smooth uniform films of gallium nitride. Now that was not achieved by anyone else at the time, and it was only because of this unique furnace design that rather than growing weird-looking crystals which were randomly oriented and created a rocky landscape at the micro scale, he was able to grow very smooth, literally atomically smooth layers on the substrate. So that brings us to the next question. What kind of substrate did he use? Well, one of the other researchers in Japan had been looking at substrates which could at least handle the high temperatures of this growth process. The growth process took place at temperatures greater than approximately 900 degrees Celsius, which is much higher than other semiconductors in the 3-5 family. And one of the materials which is very robust was sapphire. And sapphire, or aluminum oxide, is not lattice matched with gallium nitride. Its lattice constant is far different. It's about 13% different. So you have a huge lattice mismatch, but nevertheless, this one researcher in Japan found that the gallium nitride, if it actually rotated to a certain tilt angle on the substrate, could grow surprisingly large single crystal regions. And there were far fewer defects in the gallium nitride film than might be expected from such a huge lattice mismatch. So Nakamura immediately turned to aluminum oxide because he recognized the technological benefits of a substrate which was A, readily affordable. There's nothing expensive about aluminum oxide. B, it's growable. You can actually create single crystals of aluminum oxide or sapphire in the lab. And today it's used in production, and you can create wafers out of it, just like you can make wafers out of silicon. And he quickly switched to that as his substrate of choice, and his smooth film growth technique was coupled with this relatively unexpected substrate, and he was able to grow low dislocation density gallium nitride. Now, the last part of the story is another piece of good luck for Nakamura, because it turns out that the material gallium nitride is very tolerant to defects. Whereas in gallium arsenide and gallium aluminum arsenide and indium gallium aluminum phosphide, the number of defects or dislocations that you can tolerate in an LED is very small. In the case of gallium nitride, the defect level could be higher. And till this day, there's still controversy about exactly why gallium nitride is more tolerant to defects compared to the other materials. So in the chapter on LEDs, you'll find a figure which plots as a function of the number of defects in the gallium nitride. It plots the quantum efficiency, and you'll find that the quantum efficiency, which means the radiative recombination rate in gallium nitride relative to the total recombination rate, stays rather high, well above, say, 50%, to a much higher defect level than in other 3-5 semiconductors. So that was, again, an unexpected result, but it enabled the use of this highly lattice mismatched substrate to be technologically successful. So with all these ingredients in place, Nichia, the company that employed Nakamura, introduced a commercial blue LED in the early 1990s, which was a real shock to the LED world, because everybody was trying to do exactly that, but nobody could do it. And the first LEDs, as they were introduced, had a price tag in the $2,000 US range. I remember that well, because I was interested in LEDs at the time. And a little Christmas tree blue LED from Nichia for $2,000 couldn't be sold quickly enough, as all the other groups in the world tried to figure out how they did it. It took other groups years to get to the point where they had the ability to grow equivalent quality LEDs to Nichia. And in fact, many lawsuits flew backwards and forwards between Nichia and several US companies and then Taiwanese companies trying to claim a stake in this new technology. And the lawsuits actually ended up affecting Nakamura himself very much, because he was dissatisfied with Nichia as an employer, because Nichia only gave him, I believe it was $200 equivalent, for the patents that he had filed on the gallium nitride LED. They had a whole nest of patents, and the other companies, of course, were trying to infringe on the Nichia patents or to find ways around the Nichia patents. And Nakamura felt that there was really more, that he had done more for his company than the extra $200 bonus for each patent he filed. So he left, and he went to work in the USA. At one point, he worked in an American company called Cree. Cree happened to be making another substrate which was also suitable for gallium nitride. The Cree substrate was silicon carbide. Cree made silicon carbide for purposes of their own, but the silicon carbide substrate happened to have a good lattice match with gallium nitride, in fact, much better than aluminum oxide. And Cree tried to file patents of their own with Nakamura's help based on the silicon carbide substrate system to distinguish some of their IP from the Nichia IP. When Nakamura is working with Cree, he also filed a lawsuit against Nichia, his former employer, for unfairly compensating him for his invention. That lawsuit took years to come to a conclusion. My understanding is that it cost Nakamura about $8 million in legal fees, and he was able to collect $8 million in compensation. So effectively, the only people who benefited from that lawsuit were the lawyers. Anyway, to sum this up, Cree and some other companies also jumped into the LED business. Cree, until today, is a very active manufacturer of LEDs, and they use their silicon carbide substrate, which is very competitive with the aluminum oxide substrate. Most of the LEDs produced today using gallium nitride are still grown on alumina. So the blue LED has some very interesting aspects, which I should describe briefly. They're, again, covered in the chapter 6 of the book, but I just want to cover a couple of them right now. One of them has to do with the efficient recombination of electrons and holes. So in this substrate, we have the opportunity to make a double heterostructure LED. So in this case, the double heterostructure would be composed of gallium, indium arsenide. So the LEDs that Nichia produced with Nakamura actually incorporated some indium because the energy gap of gallium nitride by itself is too high. It's in the ultraviolet range. By introducing some indium, you can tune that energy gap down into the visible range. And I'll send a slide at the diagram showing the dependence of band gap on indium are in chapter 6. So if you were to substitute some indium in place of gallium, you would have this compound. I'm sorry, this should be nitride, not arsenide. And when you create the well, of course, you would have a different composition, and you would make sure that Y is larger than X because you want the band gap in the well to be smaller than the band gap of the cladding layers. And on this side, again, you'd have gallium 1 minus X, indium X, nitride. So this double heterostructure for gallium nitride works, but it didn't work as well as people expected. And there was a reason for that, a very interesting reason. What happened is that when you grow gallium nitride on a substrate, there are always some stresses involved because the lattice parameter is not identically matched to the substrate. And as a result, the stress involved causes an electric field to build up in the gallium nitride. The existence of an electric field in a crystal due to stress is well known. It's called the piezoelectric effect. And you're familiar with it because when you want to start your barbecue, you strike a material, a piezoelectric crystal, with a little hammer, which builds up very intense stresses for a very short time, and you can actually create an electric field strong enough to spark and ignite the gas. So the same stress effect exists in this gallium nitride material, leading to the formation of an electric field in the gallium nitride semiconductor. And that electric field actually shows up in this band diagram. And the electric field causes the bands to tilt. As you know, an electric field is equivalent to a slope of an energy band in an energy band diagram. Now, the effect of that slope was to cause the electrons which entered the conduction band, actually the electrons would enter from this side, to collect on the one hand side of this quantum well, or this double heterojunction well, and the holes which would have entered from this side collected on the other side of this double heterojunction. And the problem was that the probability of a recombination between an electron and a hole is the key to the performance of the LED, but it was diminished because the electrons and holes would spend time on opposite sides of the double heterojunction well. That problem meant that the radiative recombination efficiency was lower because these electrons would have a higher chance of finding a non-radiative recombination pathway, and the same with those holes. The solution to that turned out to be to narrow the width of the quantum well and to create what's actually called a quantum well, which is narrower than the traditional double heterojunction design. So by narrowing that double heterojunction, you can minimize the separation along the x-axis in this diagram. You can minimize the separation between the electron and the hole, giving them a much higher probability of a radiative recombination. Now, a few lectures ago, we discussed how the width of one of these wells is important to give enough capacity for that well to have a recombination rate. And that well width was an important component of that recombination rate. And the expression that we came up with when we were discussing that recombination rate showed that the well width